inviting me to a workshop in which I'm sure they knew that I would not talk about emergent hydrodynamics. So I will not talk about emergent hydrodynamics. I will not even talk about integrability. So those of you who think the world is all integrable and otherwise not interesting, you'll have to bear with me for 1 hour. I also thank the Institute for all the arrangements. It's always great to be here. One of my favorite places to discuss physics. Good. So I'm at Maynooth University in Ireland. I moved there 3 years ago, but it's really a heavy teaching college, so I don't do much research there. I do my research back in my previous institute where I was some years ago, together with some of the organizers and participants here. And now I fly back there, and the work I will present today is also done with current members of that institute. Good, so I'll introduce everything that's here. And I especially realized that I have to introduce the word behemoths. So what I will talk about is the eigenstate thermalization hypothesis. So thermalization in explicitly non-integrable systems, right? So again, I'm sorry to those who are only interested in integrable systems. Hopefully you'll find something of interest here as well. So it will be about the eigenstate thermalization hypothesis, and I'll in particular talk about scaling, size dependence of this object. So because the talk subject is so different from everything else here, first I will introduce this concept, this outrageous statement, which should offend you a bit, because many body Hamiltonians are particular Hamiltonians. If you write them as matrices, they're matrices with a lot of structure. If you deal with integrable matrices, they have a lot of structure. But anything that's not integrable, if you look at the Hamiltonian as a matrix, there are certain senses in which they behave as random matrices. So I will say exactly in what senses you can think of them as random matrices. So there are many different ways you can think of them as random matrices. Some ways they deviate, so we'll discuss those in some detail. Second, I'll talk about the eigenstate thermalization hypothesis, which is the main topic of the talk. It's a bit far from the main theme that we saw yesterday, but it's about dynamics. It's about thermalization when you do not have many conserved quantities, right? And there are many aspects of this ETH which have been studied in the last few years. The one I will focus on is which observables obey eigenstate thermalization hypothesis. In particular, the type of scaling that ETH usually has. Good, so then the final part will be about ETH scaling, which observables. The most physical types of observables are local observables, and then I'll construct a full class of observables. There'll be a way of constructing very non-local operators. That's what we call behemoth operators, local operators that you think of as physical, and all sorts of things in between. Good, so the first two parts are really introductory, and that will take about half the talk. And some of you will know some of this, but hopefully there'll be something new for everyone. And then the new part is this. So the introductory part is probably from some of the first papers here, and the new part is from this paper, done with two co-authors who are currently in the Max Planck Institute, Dresden. Good. So this is not really necessary, but there is a way of thinking that we'll use, which is useful to introduce. If I remind you that much of what is being done in quantum non-equilibrium physics today, a big theme, depends on the quantum systems being isolated. So this is not often stressed enough, because there is also another community which studies non-equilibrium dynamics in solids, like pump probe spectroscopy or things like this, for whom this is not true. So for all the systems we heard about yesterday, and I'm sure every dynamics talk we'll hear about in this conference, we usually talk about isolated quantum systems, meaning that there is no bath, right? This is important. That raises new questions, including the question of thermalization. And this is, in this audience, I don't have to apologize for this, but if you give a talk in a physics department with experimentalists, then you have to explain that they shouldn't be too offended, because although isolated systems don't exist in the real universe, there is a large number of experiments now where the time of measurement is much less than the time scale of environment effects. The major class of examples come from cold atoms. This one Benjamin showed yesterday. I think Alvise also showed the same thing. There's a few other experiments. There's a lot of cold atom experiments which really fall into this class. There's also some NMR experiments which you could argue more arguable, more debatable, but also fall in this, this class. Good. So I want to talk about isolated quantum systems because I'll be looking at the many-body spectrum. And if you, like me, were trained in a condensed matter theory group, then you were taught that what's interesting is the low energy part of the many-body spectrum, and you should never think of anything else. Right? That's, so that this was drilled into you, and you had to unlearn it. So when dynamics in isolation came up, many of us have unlearned this, because if you're in an isolated system and you start with, this is my cartoon of the many-body spectrum, and if you start your initial state in some combination of excited states, then you never get to the ground state. So there is reason to look at the full spectrum. Right? So we'll be talking about the full spectrum, in particular, the middle of the many-body spectrum. So this leads me to studying the middle of the many-body spectrum, and it'll also be important when we look at the eigenstate thermalization hypothesis. In particular, I will make the claim that mid-spectrum eigenstates are random in several senses, which we'll describe. When I say often, I mostly mean non-integrable systems. So that's the main exception. So the main point of this talk is something that doesn't hold for integrable systems. Good. So we'll talk about in what sense a many-body Hamiltonian matrix is a random matrix. So I'll briefly remind you of some properties of random matrices. So the relevant classes, the most relevant classes, although they're not that close to many-body Hamiltonians, are the well-known GOE and GUE classes, which, roughly speaking, are those with real elements and those with complex elements, and both being either symmetric or Hermitian. And then among the various properties, the two I will illustrate and compare with many-body systems is, number one, if you look at the eigenstates of a random matrix, then the coefficients are Gaussian distributed once it's large enough. Right? So if you take the coefficients of an eigenstate, plot a histogram, you will get a Gaussian curve. Number two, the eigenvalues have Wigner-Dyson statistics. So it's either, depending on whether you have GOE or GUE, it's one of these two forms. So there is level repulsion, meaning the distribution has zero at zero values of the level spacing. So this S is the level spacing. Yeah. So for a random matrix, it doesn't matter. For a many-body Hamiltonian, you have to, for a physical system, you have to ask that. Yeah. So at this point, it doesn't matter. Good. So this is some selection of basic properties of random matrices. So of course, you know that the kind of many-body Hamiltonian will have usually spatially local interactions and few body interactions. This results in the typical Hamiltonian matrix, if you write that out, the typical Hamiltonian matrix being sparse. So it's really not like the GOE or GUE class. So that's already one difference. And of course, the elements are not random. You create them out of a Hamiltonian. Nevertheless, if you take one of your typical many-body Hamiltonians, if it's not integrable, then usually the coefficients of the eigenstates will be Gaussian distributed. There are many exceptions to this, so I will point out some exceptions. I will show you some exceptions as well. And the energy eigenvalues will usually have Wigner-Dyson statistics. So of the many exceptions, I think the integrable systems are the biggest class. And in other audiences, I might have said integrable systems are bad, but I won't do that here. And the other exception is the edges of the spectrum. So in a physical Hamiltonian, usually the edges are very special, which means low energy and low energy eigenstates so deviate more from this random matrix class. Good. So let me illustrate these two claims that a typical many-body Hamiltonian will have these properties. So the first one is, so what I'll do is I take some model. This is a Heisenberg model, which is, XXZ chain, which is integrable. But then I break integrability by adding nearest neighbor terms. And I also I will take finite chains, L sites. And I also break reflection symmetry by, I dropped one of the first next nearest neighbor terms to break reflection. So this is because symmetries are annoying, so I get rid of them to start with. Then I have to choose a basis to express the Hamiltonian. And the things I will say works in many bases, unless, of course, you choose the eigenstate basis. That's really. So I will choose what's known as configuration basis or exact diagonalization basis. Anyone who has diagonalized a many-body Hamiltonian usually uses this basis, not 100% of the time, but this is the basis of real space configurations. Good. So I will look at eigenstates of this Hamiltonian, which I expand in this basis, right? So please remember this notation for the configuration space basis. When you do something more serious, we'll use that notation. So I'll look at these eigenstates, coefficients, and if you look at them, so I plotted the histogram of, the histogram of the eigenstates slightly rescaled, don't worry about it. So D is the Hilbert space dimension because this is a finite Hilbert space system. And then all these curves are histograms, although I've just drawn them continuously. And then the thing to notice is, in the integrable case, so if I set the next nearest neighbor term to be 0, then this black curve is Gaussian. No part of the spectrum, the middle, lower, or upper part, no part of the spectrum follows a Gaussian distribution. So the coefficients are all non-Gaussian. They're really non-generic for an integrable system. Whether you are at the middle of the spectrum, lower part of the spectrum, or top of the spectrum. In a non-integrable system, if you look at the lower or upper part of the spectrum, so that's the green and blue lines, those are not Gaussian, but the middle of the spectrum, I took 200 eigenstates in the middle of the spectrum, took all the coefficients, and then just plotted the histogram. That's very close to a Gaussian. So that's the sense in which a many-body system is like a random matrix. The middle of the spectrum eigenstates are random-like. The rest is not. Not the bottom part and not the top part. Sorry. So for a finite size, there is nothing sudden, and yeah. So it gradually moves from one to the other. Maybe I have examples like that in a couple of slides. So notice it's not completely Gaussian. So even a non-integrable spectrum is not completely random. There's still some structure, and you can think about this type of structure for, and I'll show ways in which it's worth thinking about. Good question. I believe not, but I'm not sure. Sorry, in a thermodynamic limit is sharp, yes. Yeah. So at any finite sizes, it's not sharp. That's the point, yeah. Yeah, this is too general a question to answer yes or no, so I'll be careful. It depends on the basis. So I'm sure you can find a basis where you will break this, but I think for a generic basis, this is more or less stays like this. I think if we start classifying the bases that are possible, it will take a long time. So I don't want to say anything, if that's okay. Yeah, so I think if you take a generic local basis, you'll find the same story. I can't prove it really because you can't check all the bases, but yeah. Okay? Okay. Yeah. Sorry, so this is, I took 200 eigenstates at the middle of the eigenstate, middle of the spectrum. Lower is I took 200 eigenstates at the, starting from the bottom of the, yeah. And the higher is, upper is, I took the top, top 200 eigenstates. They're more or less similar, right? I mean, they're not non-Gaussian. They're both non-generic. So I don't know why exactly what. So it's not particle-hole symmetric, and it's not. It becomes a ferromagnet like Hamiltonian, but exactly what happens, I don't know. And I think the filling is, it's probably 15 sites, and I didn't write it, and 7 up particles or something like this. So it's, yeah, it's at a fixed filling, yeah. Good. So this is what I said about level statistics, that if you look at a random matrix, you get the GOE statistics if it's real coefficients. So the same model, I'm now tuning, so this XXZ, which is integrable, on the left is integrable, and this is the non-integrable region. And I'm now looking at something that became popular last 10 years or so, not the level statistics itself, but something that characterizes the same thing. I think many of you know this, but you can, so it's generated from the level spacings. And then it has particular values for GOE and for Poisson, and you really see that as you go away from integrable models, you get the random matrix behavior, right? So, yeah. This quantity. So you take the levels, and then you take the ratios of successive levels. Yeah. So it's the ratios. Yeah. Yeah. Sorry. Go. So this is for the eigenstates. So which, yeah. So you don't need to order them. You just take all the coefficients, and then you draw a histogram of that. The ordering doesn't matter. Yeah. Yeah. So the ordering doesn't matter. And here it's just about the eigenvalues. Okay. And then you also see that the integrable models have a different. Yeah. Go ahead. So I think what happens, that's a bit complicated. I think what happens is that at that in that region you can neglect the nearest neighbor part, and the next nearest neighbor part is important. Then it becomes something like two decoupled, so the odd sites and the even sites, and then analyzing that is a bit complicated. But I forget if it comes and stabilizes at Poisson or something else happens. But so it's like two decoupled Heisenberg chains. Good. So final example, looking at this idea that many-body Hamiltonians are random matrices. So this one is a slightly different model where I used XYZ, which is also integrable with this, what's that called? The more complicated Bethe ansatz. Sorry, yeah, so it's like the 8-vertex model, not the 6. So, but then it's also integrable. But then I did the same trick. I used a next nearest neighbor interaction, which causes the whole thing to be non-integrable. And what I did here is I took the full spectrum from the lowest energy to the largest energy, and then calculated the entanglement between, let's say, the two blocks of the chain, right? Actually, I also did, one is a block entanglement, the other, which I call a comb entanglement, that's between sublattice A and sublattice B. So the difference doesn't really matter so much. What you see is, again, the middle of the spectrum has a high entanglement. You expect this because middle of the spectrum is volume law, lower part is area law, etc. But then what you see on top of that is that they reach a value which is very close to what's known as the page value. That's the value you get if you take random matrix eigenstates, interpret that as a many-body basis, and then calculate the entanglement. Then you get on average, the page value with some fluctuations around it. So a random matrix would have, on average, this entanglement, the green curve. So you see that the middle of the spectrum of a many-body system is very close to having random matrix entanglement, right? So that's another way you can see that middle of the spectrum of a many-body system is random matrix-like. But then you see all the warnings as well. The bottom of the spectrum or the top of the spectrum, they are not random matrix-like. They are in some ways a bit more like integrable eigenstates, not in any mathematically precise sense, but in the sense that they deviate a lot from random matrix systems and have a lot of structure. There is still some deviation. That means even in the middle of the spectrum, there is some structure, some memory of the fact that these are eigenstates of a local Hamiltonian. And you can, so we are currently looking at trying to understand that kinds of deviations in various ways. So there are, I showed you 3 things: eigenstate coefficients, level statistics, entanglement. You could look at a dozen other properties of eigenstates, and the picture that emerges is this. Middle of the spectrum eigenstates are pretty much random eigenstates. The bottom of the spectrum is not. In an integrable model, all eigenstates deviate strongly from random matrices. Yep. So in the infinite limit, you probably have a lot of degeneracy. But in a finite system like this, I guess the Hilbert space here is several thousand. I don't remember exactly. This is probably 4,000 or so. Among the 4,000 states, there are not that many exact degeneracies in the spectrum. So I hope that answers the question. That's correct. Yes. Yeah. So if you have degeneracies, defining entanglement is a bit problematic, but mostly it doesn't appear in finite matrices that you can do on a computer. So usually, it could appear on X. Yeah. Sorry. Yeah. So mostly at these sizes, it doesn't really appear. Good. So I'm more or less done with my my statement that many-body Hamiltonians are random matrices. Go ahead. Yeah. Or you take lots of random states and then take the entanglement in each of them, calculate the entanglement in each of them. They will have some distribution, and that page will be this. Yeah. And the distribution is small. It also goes down as square root of the Hilbert space size. Okay. Any other questions? I'll change topics now. So the next topic is thermalization, which hasn't really been talked about in the workshop yet in terms of generic non-integrable systems. So, but then I think this is something very well known by now. So you can talk about thermalization in various ways, in terms of a reduced density matrix of some part of it or so on. I'm thinking of a isolated system described by a pure state that's evolving. I will describe thermalization in terms of an observable. And that means that you start in a non-equilibrium state after a quench or so, and any observable oscillates and eventually relaxes. Relaxation is not thermalization. Thermalization means that the value to which it relaxes, the observable relaxes, is the value you get out of a thermal ensemble. So this is the value to which the observable O relaxes. I realize I didn't introduce this. I'll do that. And this is the thermal ensemble value. So this is the statement of thermalization. So I think the definition I'm missing is that I have an initial state which I expand in terms of all the eigenstates of the Hamiltonian with which I evolve. So C's are those coefficients. And so This is clearly a mad statement, right? These are such different, different coefficients. There's no reason for this to be generically true. The reason it's generically true is that the matrix elements of many operators in many body systems have a particular property. That's known as the Eigenstate Thermalization hypothesis. I'll state it in two versions next, but then maybe I should first notice that from numerical work in the past 10 years or so, in many non-integrable systems, people including me have looked at many observables, and thermalization is very generic, right, for many types of observables in many non-integrable systems. So it's now commonly thought of, thermalization is commonly thought of in terms of the eigenstate thermalization hypothesis. And one part of the hypothesis is that these matrix elements, you take an observable, you calculate its matrix element in every eigenstate. So these objects, those are smooth functions of the eigenenergies. So that's one partial statement of the eigenstate thermalization hypothesis. I'll call it the ETH. It was introduced by papers here with some precursors before that as well, and made very popular by this paper about 10 plus years ago. I'll give you an example from this paper, from my work in a minute. Here's a more sophisticated statement of ETH. And I've stared at this more than I want to admit, but there are some things here that are still mysterious. So the idea is that if you look at an observable in a many-body system and look at its off-diagonal matrix element, then the physics of the system is contained in some smooth function of energy. That's what I said before, that the diagonal matrix elements are smooth functions of energy, and the but then in addition to this smooth function, there is some fluctuation term, which is usually written like this as a Gaussian random variable, and then there is also the off-diagonal part, which is also supposed to have some smooth dependence of energy. The details of this function are not yet extremely well understood, I would say. What's important is this factor, which appears in Strednich's paper first. I find this totally mysterious. Everyone seems to have their own own way of understanding this. The way I understand it, because I work with finite Hilbert space systems, I understand it as I think of the entropy. So entropy in a finite quantum system is a bit, well, I find it a bit problematic. I think of it as something that goes as the log of the Hilbert space size. You can think of it in terms of the density of states if you want. But then for finite Hilbert space, this seems to work well. That means that both the diagonal matrix elements and the off-diagonal matrix elements, they are distributed with this width. So you get a scaling with the Hilbert space size out of this. And there are several ways you can argue this. Several of these ways of arguing d to the minus half scaling goes back to expecting states to be random in the senses that we've talked before. So the thing we'll take away from here is that both diagonal and off-diagonal matrix elements of local operators or of operators, we'll talk about what types of operators, have distributions, if you take them and plot them as a histogram, which go as d to the minus half. D is the Hilbert space dimension. Yes. Average, yeah. Yeah, so I think the operational way of dealing with it is to look at a small energy window where these functions are not widely varying. Yeah. I would imagine that the power doesn't depend on energy, but the coefficient could depend on energy. Is that what you meant? Or? Yeah, so there will be a coefficient which is energy dependent, but the power is independent. Yeah. So the power is the more fundamental part, and we'll focus on that in the rest of the talk. Good. So, let me give an example of ETH where I took some system. It doesn't really matter what. What I took was an XXZ chain and then broke integrability with having a parabolic magnetic field on top of that. I think I was motivated at that time by this Weiss experiment, right? How does a parabolic potential break integrability? So it does break integrability. You have to be a bit careful about how you scale this system, but we've thought about that. That's under control. So what you can do is look at some observable. The observable I looked at is the sum of SZ values in the middle 1/3 of these systems. That's why you have 12, 15, and 18 sites. And if I look at those, look at that observable, calculate the diagonal matrix elements, they are distributed in some way. But then if I look at it as a system size dependent distribution, then you see that the width of this goes down and further down. And if you analyze that, it's a bit challenging because you don't have that many system sizes that you could look at the full spectrum of, right? But you find d to the minus half scaling. And when we first found this, I argued this based on some kind of randomness assumption of the coefficients, of eigenstates. So this is consistent with what we got out of Srednicki's entropy, finite quantum system entropy. Very good. So this is more or less the standard understanding of ETH. I'll now move on to ask about which operators will obey ETH, but now I have a more precise way of saying what is ETH. ETH is when an operator has diagonal or off-diagonal matrix elements that scale as d to the minus half, right? So we'll talk about that next. Was there something else here? Nope, I think yeah. Right, yeah. If you plot them as a distribution, then the width of the distribution, yeah. Good. So, so in order to do this, in order to look at large classes of operators, the operators. So usually people have focused on local operators. So here, it was a sum of local operators. I took the Z values and took the sum over different instances. But then you immediately ask, does it have to be only local operators? And I'll try to answer that by thinking about random matrix theory a bit, calculating distributions of operators in random matrix theory, and then drawing an analogy to many-body physics. The way I do this, the way I do this is I take this interpretation of random matrices. You can interpret a random matrix in many different ways. Previously, we interpreted it as the random matrix basis was the many-body configuration. So now I will do something simpler. I will think of a random matrix as a Hamiltonian of a single particle on a fully connected graph with random hoppings, right? And then it will be Hermitian, so it has this Hermitian properties. So this is my random matrix Hamiltonian. It's a single particle Hamiltonian, so you might say it's overkill to write it with second quantized operators. It is, but it's what I'm used to writing Hamiltonians as. So I will think of this single particle Hamiltonian. Okay, now that you have a single particle Hamiltonian on a fully connected graph, see, this is if the hoppings are randomly Gaussian distributed, then this is a GOE matrix, right? So now that I have this interpretation, I could ask, what observables do I have in such a system, in a single system with random hoppings? It's too simple, right? So there are not really many observables you could ask about. The only one I can think of is the thing that appears in the Hamiltonian, the hopping, or the site-to-site correlator, if you want, single particle site-to-site correlator, okay? Let me write it like this. Each of these is a node in this. So this is the node-node correlation function, and we can think of its distribution, right? Let's think of its distribution, and I will connect to many-body systems after that. Good. So this is the kind of operators I'm looking at. And it's an operator. That means it's a matrix. As a matrix, this is just one in the matrix, and the rest is 0, right? Very simple matrix. But then also a very powerful matrix, because it's the class of these matrices are the basis for all operators. And you can, if you want, you can think about the non-Hermitian version, because I was taught that operators have to be Hermitian. I teach that myself. So that has 2 non-zero elements instead of 1. Good, but let's think about the one with 1 non-zero element. That's convenient to think about. Good, so this kind of operator. What's the many-body analog? In our many-body analogy to random matrices, we thought of the basis states of the matrix as many-body configurations, right? Real space configurations. That means you can think of the same graph, the many-body graph, as something where each node is a many-body configuration. Let's do it in real space, but if somebody wants, you can also look at some other basis. But I will just use the real space configuration basis. Okay? So then the corresponding operator is this operator. It takes one many-body configuration and changes it completely to another many-body configuration. This is a highly non-local operator, and because I had an English-speaking co-author, he came up with a name for something that's highly non-local, huge. It's something from the Bible, which is, I think the Bible describes the behemoth as a land animal, which is just huge, right? So he came up with this, very good. The editors didn't complain, so it's now published with this word in the title. I'm very proud of that. So now in the many-body system, this is what I'll call a behemoth operator, and it'll be useful. It'll be useful because first of all, it forms a basis for all operators, and I can calculate its distributions easily. So any operator is a sum of such operators, and in configuration space, it looks like this. So just 1, 1, and the rest zeros. That's why it's a basis. Good. So now you want to think in physical terms. In physical terms, a behemoth operator, which takes one configuration and turns it into another, is something like this. If you have spinless fermions, it could take a configuration like this and turn it into a configuration like this. If it's a spin-half lattice, it could take a configuration like this, turn it into something like this. A Bose-Hubbard, it could take, so it really takes a big configuration, turns into something else, not your typical operator. If you want to write it in terms of second quantization, it looks complicated, but you see that it's highly non-local, right? It takes, it's a n point correlator where there's n sites on the system. Good. Right, exactly. So that's what we'll do now, yeah. Yeah, so this itself is non-local, but its finite sums contain everything. Good. So the way to get to our operators, the things we know, is to take these behemoths and form the appropriate sum. You have to do it appropriately, not randomly. But if you do the appropriate sum, you can create anything. You can create any 2n-point correlator, or even a 2-point correlator, which is what we want to go after, right? That's a physical operator, 2-point correlator. And you can do some counting, and if you do the counting, you see that if you want to get a 2-point correlator, then you need order D of these behemoths that you sum, right? And then if you want and the behemoth itself is there's just one term, one behemoth, or 2 if you want a Hermitian part. And then you can do most of this for, you can check this, sorry, you can now, so let me say it here. Now that I want to look at distributions of these objects, the trick I will use is I will go back to my random matrix description in terms of a single particle Hamiltonian, and then I will calculate the distribution of these objects, which are the random matrix single particle picture, and this is the many-body picture. And then if the many-body Hamiltonian is like a random matrix, it'll obey whatever distribution I derive. Very good. If I now take the random matrix distribution, this is the kind of thing, if you open a review or book on random matrices, the kind of integral you get all the time, how you calculate distributions of variables made up of, so basic probability of distribution of variables composed of other variables. So if I look at the behemoths, their off-diagonal correlators are products of two coefficients. Each coefficient is Gaussian, is a Gaussian random variable. So you can calculate the distribution of a product of a Gaussian variable, of two Gaussian variables. You get a Bessel function. Since I never remember all the types of Bessel functions, this one looks like, I think it's the third kind of, I forget, modified of second kind or third kind, I forget which one. It has a log singularity and goes down as exponential. This is the distribution of the behemoth operators. Of course, we will need not these funny operators, they're really strange operators, but we use them as a basis, right? So we want to know what's this distribution of a sum of m of them. So I could sum two of them, and I go from a Bessel function to an exponential distribution. I could sum m of them, and I get a smoother and smoother distribution. In particular, if I do 5, this becomes smooth. The tail is still exponential. If I have more and more, the Gaussian part eats the exponential part, and that's the central limit theorem in action, right? So you sum more and more random variables, you end up with a Gaussian distribution. And you can work out much of that analytically, which if you have the right collaborators, it's too painful for me. Good, so you can now test the idea on a many-body Hamiltonian. So here is a many-body Hamiltonian, the same one I used before, with a particular number of upspins and sites. And if I look at the non-Hermitian behemoth, which takes you from this configuration to this configuration, the zeros are downs and the ones are ups, then I can do that numerically, right? I take my eigenstates, I plot all the off-diagonal matrix elements of this behemoth operator, and I draw a histogram. This is the histogram. And you see that it follows the random matrix prediction quite well. So this is no surprise, because we showed already that the middle of the spectrum of this model or any other many-body non-integrable model is very much random-like, right? So, yeah. Okay. So there are some operators which are a bit tricky. So this idea that every eigenstate is random-like and every operator is random-like is clearly not true. There is some physics in the model. So there are some operators which are tricky. So what I do is I want to take typical behemoth operators. So I just use samples of many of them, and I will show you some results of those before we go to local operators. Okay, so still in these very unphysical but useful class of operators. I did this, sorry, was there a question? No. I did this for various models with, this is a spinless fermion, nearest neighbor, next nearest neighbor interactions with some Stark field, with some electric field. This is a Bose-Hubbard chain. This is a Bose-Hubbard ladder, yeah, just on a ladder geometry, and so on. And it's generally true that these systems, as long as you stay away from integrability, usually you can figure out how to do that. As long as you stay away from integrability, you get the distributions that are predicted by random matrix theory, which are the green curves here. Good. So still these very unphysical operators. I think we want to go to physics. So what we have found out that the behemoth distribution has a width which scales as d to the minus 1. So that was in the formula. I didn't talk about it. So these unphysical operators actually have super ETH scaling. They're very good thermalizers. So if you take these observables, they thermalize very, very well, even in medium-sized systems. Now, local operators, what we are interested in, is a sum of this many behemoths. M was how many of them I'm summing, right? And then you can use the central limit theorem to figure out that the scaling of such an operator will be, well, square root of m times d to the minus 1, so it's d to the minus half. So that's how you get ETH scaling. You can get it out of thinking about which operators are local. Local operators are those which you get by summing over d of these super operators. Okay, so this is really the physics part. So I think the thing to learn about local operators are, number one, ETH works because physical operators are, actually, I need this part. So d to the minus half scaling works because local operators have this many terms in them. Now, if I forgot about physics and just wanted to construct a typical operator, that means I take a matrix, I fill it up with elements, right? That's not how you do physics, but that's how you think of random matrix theory. So a typical operator would be dense, meaning more than d of it would be filled. Maybe of the order of d squared would be filled, right? So it's a d by d matrix. And then you get a scaling which is sub-ETH scaling. So it goes, you get d to the minus less than half scaling. So a typical operator will not, in this sense, in this artificial probabilistic sense, where you just fill up a operator matrix, that will not obey ETH, that will not thermalize. But either the behemoth, the very special non-local operators, or local operators will thermalize in the senses mentioned here. The reason ETH works in this way of thinking about it, the reason ETH works is that physical operators are sparse. So that's why you get thermalizing scaling. Yeah. Yeah. Well, I mean, you could say that it thermalizes. So in some loose sense, integrable systems also thermalize. Right? So I just mean in the ETH sense, thermalization is when you have this scaling. So that's a bit stronger than, yeah. Yeah. Right. Yeah. So so you couldn't write it in the form. Yeah. Okay. So here is going from a highly non-local behemoth operator, adding many of them to get, this is also a highly non-local operator. So by, by small n, I mean when small n equals 1, that's a C dagger C. Small n equals 2 is C dagger C dagger C C. And small n equals 7 is a pretty non-local operator. C dagger C dagger C dagger C dagger, 7 of them, and then 7 C's. Right? Of course, it's XZ, so those are S plus, S minus, but I use the language interchangeably. This is a single behemoth, which is Hermitian. So you see how the distributions change as you go from non-local to local. So in the these are super ETH, so it's already very sharp, whereas a local operator is less sharp. If you look at the scale, the funny thing is, if you look at the local operator, this is my prediction, and this is what I get from an actual physical Hamiltonian. The order of magnitude is correct, but there is some deviation. That means the physical system still remembers that it's a local Hamiltonian and it's not completely random. It has some structure which causes correlations, which causes slight deviations from the central limit theorem. Some partial deviation of the central limit theorem. So it's hard to characterize in more precise terms. So I don't know. So in the sizes that we could see, I couldn't really see that it goes away. So I think that's related to the question of whether a physical Hamiltonian becomes more random at larger sizes. And the answer is not clear to me yet. Okay. So if you look at systems which are not RMT, the most typical are, I guess, MBL, which is fashionable in other communities, not this one, and integrable models. So the B and C are non-RMT systems, non-generic systems. So you see that the typical distributions vary, in this case, very widely. This is because MBL systems have a power law distribution of coefficients. I don't know who that comes from. I think it was Andrea De Luca and someone. So, and then integrable models is not as pronounced a deviation, but they're not random. They remind you that they're not random. So, so these are behemoth distributions for non-RMT systems. Very good. So I'm done. I'm happy to take questions. Thank you.
Any question?
These poorly scaling operators